So all of this led to the work of Schrodinger, who was one of the great scientists of all time. And Schrodinger on a personal level is just absolutely fascinating, but we don't need to go into that here. So Schrodinger took the work of de Broglie and lots of other people and created what are called now the Schrodinger equations. And Schrodinger equations are basically fancy mathematical expressions of waves. And these wave functions get this symbol psi, which is like another Greek letter and stuff like that you don't need to know. Now, psi is really cool because it describes the motion of the electron waves with location and time. And the quantization that Bohr introduced kind of artificially came out naturally when Schrodinger did that. So Schrodinger's wave equations are super powerful. If you have taken at Mount Hood Community College Math 254, which is Calculus 4, and you've done multivariable calculus, stuff like that, you would be able to solve the Schrodinger wave equations. Now, it may be something you have to do a little research on, but it is something that's totally doable. And it's a fascinating science, fascinating mathematics. We'll talk about the results of Schrodinger's work here without actually doing the math. So if you haven't taken Math 254, don't panic or anything like that. It will just talk about the results of it, which is pretty cool too. So these wave functions are basically functions of distance and two angles. And spherical coordinate systems is what they usually use. And each of those wave function size corresponds to what we're going to call an orbital. And an orbital is just a region of space around the atom where the electrons can be found. Now, psi itself doesn't describe the exact location of the electron because that's hard to know. But if you take psi squared, then you get the probability of where the electron's going to be, which is pretty cool. So psi squared will give us the probability, like where the electrons are most of the time. We won't know exactly where they are because we're more interested in the energy, but we will at least have an idea of where they are. A lot of the times, that's where the orbital pictures will come in. So again, scientists and chemists, we always make the choice for energy over position. So we're going to know the energies of these electrons pretty well, but the probability of where the electron is the best we can do under these circumstances.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
So this is kind of a pet peeve amongst chemists, but in reality, if you want the ultimate description of how an atom looks, all right, that would be it. It would be kind of the nucleus in the middle, and that's, by the way, way too big for the atom, but let's not worry about that. It would be the nucleus in the middle, and there'd be kind of like a shimmering kind of energy-looking thing around it, and that's where the electron is most of the time, the probability of where the electron is. Now, in the Bohr model of the atom, which is sometimes seen as kind of like electrons around the sun, kind of thing, like electrons around the nucleus, like planets around the sun. But that doesn't really work because, again, problems with classical physics led to that. So the atom, how we describe the atom, has gone through lots of changes over time, all right? And it's very difficult as a teacher to draw like shimmering electrons around the nucleus. So that's why a lot of times people will use the planets around the sun version of the atom, which is fine. But just realizing in your own mind that's not really correct, all right? We have a better model, but it's harder to draw. People need models to talk about theories and concepts. I dig it. But now that you are hip chemists, you know that in reality, electrons are shimmering around all the time. Pretty cool stuff. Quantum mechanics involves just some math equations, Math 254 kind of stuff, but nothing we're going to do in this class, all right? And those electrons, what happens is they exist in these discrete levels around them called shells, all right? So the quantization that Bohr introduced, those n values, those are called shell numbers, and they're pretty cool. And the energy of the electrons can basically, when you look at the whole thing of quantum mechanics, it can be described through a set of 4 quantum numbers. And the 4 quantum numbers are n, L, M sub L, and M sub S. So N is called the shell number, L is called the subshell, M sub L is called the orbital, and M sub S is called the spin. Now, subshells are L. A lot of times it's the cursive L, but sometimes it's just a regular L, so it kind of looks like a 1. Just be aware of that. Now, shell numbers come from Bohr. Those are whole numbers, 1, 2, 3, 4, all the way up to infinity. N equals 1 is closest to the nucleus, and N equals 2 would be farther, N equals 3 would be farther than that, stuff like that. L, subshell numbers, always go from 0 up to n minus 1. You can think of subshell as like a special edition, subset, if you will, of the shell number, because L depends on n. And L values, we're going to see, have some things that are pretty common, but they always start at 0. So an L of 0 doesn't mean it doesn't exist. It just means that's actually a valid value of L. L goes from 0 up to n minus 1. Now, M sub L depends on L, just like L depends on n. M sub L represents the number of orbitals, the number of places that electrons can be around the nucleus. M sub L goes from minus L to positive L, and an M sub L value of 0, again, doesn't mean it's nothing. That's actually a valid number for M sub L. And M sub S is the spin quantum number. It only has two numbers, positive 1/2 and negative 1/2. So what we're going to do in this lecture is we're going to first look at shells and subshells, then we'll talk about orbitals, and then finally we'll talk about the spin quantum number and how those apply. But if you step back for just a second, those 4 quantum numbers describe the energies of these electrons super well. And it does a great job in describing the probability of where the electron's going to be around the atom also very well. So it's a credible testament to science. And again, going back to Lord Kelvin's cloud speech, this is nothing that was known at his time. So again, he was just being so arrogant and stuff. Keep doing what you're doing, follow what you love, all that kind of jazz. So that principal quantum number n, which is also called the shell, it helps describe the energy and the distance from the nucleus. So in that picture right there, n equals 1 would be the closest shell to the nucleus, 2 would be a little further, 3 would be further out, and stuff like that. N values are always positive. They're always just basically circles that go from the nucleus. Now in the periodic table, you can actually see the shell numbers in effect. And we'll talk more about this later, but the period numbers on a periodic table go left to right. And n equals 1 is going to be hydrogen and helium, the first two. N equals 2 is going to be lithium, number 3, over to neon, number 10. N equals 3 starts with sodium, Na, etc., etc. And so you can actually see an implication of the shell number on the periodic table. And we'll talk more about this later. It's really just for main group metals and non-metals, not those transition metals, which we'll talk about soon, but the shell number has a direct effect on the periodic table. The L value, the angular momentum number, or the subshell number, helps to describe what the shape of the orbital looks like. Now, we'll talk about this here pretty soon, but we're going to talk a lot about S, P, D, and Fs in a little bit. And all the S ones are basically spheres, and the Ps look kind of like a figure 8, if you will. Ds look kind of like 2 figure 8s together, and Fs look like 3 figure 8s. This has to do with the subshell. Now, L values always go from 0 up to n minus 1. So the L values will be limited to n. Also realize that L and n will not have the same number. So if n, for example, equals 2, you will not have an L value equals 2. They're never going to be the same part, and that'll be important to us coming up. L values oftentimes do use letters. So the S, P, D, F values down there actually refer to different values of L, and we'll talk about why this is the case. So in chemistry 221 and on, a lot of times people use this S, P, D, F, G kind of ratio, and there's different expressions for it. But the S value means L equals 0. So when you see like S values in the lower left-hand corner, that means that your L equals 0. And when you see P, that means L equals 1. So notice that L equals 0 is going to be like a sphere. That's where the S comes from. L equals 1 looks like that figure 8. People call it a dumbbell. Whatever, that doesn't work for me, but that's fine. Anyway, L equals 2 is the D. That's like 2 figure eights. Sometimes people call it a clover. L equals 3, I don't know of a name. I call it 3 figure eights, whatever. L equals 4, you can imagine would oftentimes be 4 figure eights, etc., etc. But SPDFG corresponds to L's of 0, 1, 2, 3, 4. And this is going to be an important thing to know / memorize. We're going to talk about the letters that go along with L. They're going to be pretty important, and we'll talk about why you can't have L just be a number by itself in a little bit. The magnetic quantum number, or m sub L value, is really where the orbitals come from. And orbitals are pretty cool. Orbitals help describe the orientation of the orbital itself. So it helps you to know what the orbital looks like and also what the orientation is. M sub L values depend on L, and they always go from minus L to plus L. All right? So this little table in the lower left-hand corner, if L equals 0, minus L to plus L would be minus 0 to plus 0. Only one value of m sub L, which is 0. And that 0 counts, so there's one m sub L value. That means there's one orbital. On the other hand, when you get to L equals 3, then m sub L goes from minus 3 to positive 3 in whole numbers. So minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. 7 allowed m sub L values. That means there's 7 orbitals. All right, and each of those orbitals would have its own orientation. When L equals 1, m sub L can be minus 1, 0, and plus 1. And those L values correspond to the directions. So you can have one along the z-axis, you can have one along the x-axis, and one along the y-axis. So there's different uses of these things. We'll talk more about them as we go through this class.
Any spinning electric charge creates a magnetic field. Spinning electrons produce magnetic fields with an identifiable magnetic polar orientation, so-called north or south. The polar orientation of a given electron is determined by the direction of its spin.
The spin quantum number was the last quantum number to kind of be detailed and figured out. But spin quantum numbers basically refer to how electrons are spinning. Electrons are always moving around, all right, like a rotation of a planet, all right? But the rotation can be with the magnetic field, which is like an example right here. So if the magnet is pointing up, it would be with the field. That would be spin positive 1. On the other hand, the spin can be against the field. That would be the second one. That would be spin minus 1. So you can think of positive 1 as being with the field and minus 1 being against the field. And if you have that, then that's what describes the spin. It's kind of hard to describe spin other than this, but you can think about it as being with the spin or against the spin. You want to usually put positive 1/2 values first. It's a little bit lower energy than the minus 1/2 value. So start with positive 1/2, go to minus 1/2. We'll talk about this more in a little bit. Magnetism can be described through spin. If you have a system that's diamagnetic, then all of the spin ups, which are represented here by red arrows, are canceled by a spin down, represented by blue arrows. And if you have a diamagnetic system, there's no interest in magnetic fields. And most things around us are diamagnetic. Every up has a down, and they're not interested in magnets. And again, most of the things around us are diamagnetic. However, you can have what's called a paramagnetic system. And a paramagnetic system means that you have some spin, up, down, left, right, forward, backward, whatever. It's not canceled out by its opposite. So if you have more ups than downs, more lefts than rights, whatever, you're going to have some unpaired spins. And paramagnetic systems are attracted to magnetic fields. So paramagnetic systems are more reactive. We will talk about paramagnetic systems more. A lot of paramagnetic systems are kind of troublemakers in the chemical community. They'll cause reactions to happen that shouldn't be. Arguably, paramagnetic systems cause us to age because it degrades our systems. Very interesting. Diamagnetic systems just sit there. Paramagnetic systems are quite reactive.
Different materials have different magnetic properties. Liquid nitrogen is diamagnetic and is not attracted to the magnet. Liquid oxygen is paramagnetic. Paramagnetic substances, in the liquid or solid state, are generally attracted to magnetic fields. Liquid oxygen is held by the magnetic field.
This is a difference between paramagnetic and diamagnetic systems. Now we're going to see in the next chapter how liquid nitrogen is actually diamagnetic. And you can see when it was poured through the magnet, it would just went straight on through, like water would or something like that. They're not attracted to magnets. But liquid oxygen, O2, is paramagnetic. It has unpaired electrons, and it actually stuck in the middle of the magnet there. That's the power of the paramagnetic system. Now, on the little picture right there, those little arrows, the green arrows, those represent electrons. And so you can see on the left-hand side, you have 1 and 2 unpaired electrons, like you have an up electron without a down. If you have even 1 unpaired electron, that's a paramagnetic system, and those will be more reactive to magnetic fields and more reactive in general. Now on the right-hand side, all of the up arrows have a down arrow, all right, the S's and the P's. So that would be a diamagnetic material. It wouldn't be interested in magnetic fields. So the spin is really important. So again, spin up means usually positive 1/2. Spin down is minus 1/2. You always write the positive 1/2, the up ones first. And if you have even 1 unpaired electron, it's paramagnetic. But if every up has a down, then it's a diamagnetic and not interested in magnetic fields. So this is kind of an overview of the quantum numbers, N, L, M sub L, and M sub S. Again, N whole numbers, 1, 2, 3, 4, represents the shell, the energies, stuff like that. The angular momentum, L, goes from 0 up to N minus 1, all right, but it never goes to N. N and L will be different. L values have SPDF notation to them. It's important to know about that. M sub L are the orbital numbers. They go from minus L to positive L. And 0, by the way, is a valid version for both M sub L and L. But finally, M sub S, the spin number, positive and minus 1/2 only. You always start with the up arrows, the positive 1/2, then you go to the down arrows, minus 1/2 if there's leftover ones. So here's a question you might see. It says, which of the following is not a valid set of quantum numbers? So what I would do on these kind of problems is you just start left and move right. So N values always have to be whole numbers greater than 0. And on A, B, C, and D, all of those are valid N numbers. Like you don't see a 0, you don't see a negative N. That's good. Now, L values have to be no bigger than N minus 1. So on A, L of 1, that's less than N equals 4, so that's okay. On B, L equals 5, that's okay too because that's less than 6. But on C, you can see that L equals 2 and N equals 2, and N and L cannot be the same value. So the problem child on this problem set is C because N and L cannot be the same. If you needed to keep going, M sub L has to be between positive L, and negative L. So on A, that works because minus 1 is between L of 1 and L of minus 1, if you will. That's okay. And M sub S can only be positive 1/2 or negative 1/2, and all of those values are legit as well.